Welcome to Quiet Science Journeys. Tonight, imagine the universe as a film with no rewind button. Not because the camera is broken, but because the story itself leaves marks that do not gather back into their original places. A star brightens, burns, and dims. Light that once clung to the surface of hot matter slips away into space. It spreads into a wider and wider sphere. A cloud of gas changes its texture almost imperceptibly. A spiral arm in a galaxy holds its shape for a while. Then over long spans, the pattern drifts and rearranges. Even in the quietest regions, warmth migrates. Gradients soften. Crisp distinctions blur into gentle averages. It is easy to mistake this for a habit of clocks. We see hands move. We hear seconds tick. We learn to name the direction those ticks prefer. But the deeper puzzle is not about the instruments. It is about the world itself. Why do so many processes come with a built-in sense of after? As if nature is more comfortable going one way than the other. If you watch a glass shatter and then watch the footage in reverse, it can look almost elegant. Fragments rise, edges knit, a solid cup reappears in the air. The scene snaps back into order. The reversal feels plausible because the screen gives you a perfect sequence of images. And the perfect sequence hides what the world had to do to make those images possible in the first place. This is the distinction that will guide the whole journey. A reversed movie is not the same thing as a reversed universe. A movie can be reordered frame by frame. A universe would need every ripple, every stray photon, every whisper of heat, and every microscopic jostle to run backward in concert. It would have to happen without missing a beat. The reversal would have to include not only the main event you are watching, it would also have to include the shadow that event casts into everything around it, the warm air, the vibrations in the table, the faint sound that dies into the room, the light that bounces, scatters, and fails to return along the same paths. In everyday life, we rarely notice those shadows. They feel like background, but they are not optional. They are the record the world keeps, even when no one is writing anything down. Now lift that idea to the scale of the cosmos. The universe is full of records. Starlight streaming outward is a record of reactions that happen deep inside stars. A cooled glow that fills space is a record of a young universe that was once hotter and denser. Chemical fingerprints in old gas clouds are records of earlier generations of suns. The distribution of galaxies across immense distances is a record of how tiny early irregularities grew into structure. These records do not point both ways. They accumulate. They spread. They persist as traces that are easier to create than to erase. So when we ask, why does time only move forward? We are not asking why the universe allows sequences. We are asking why the universe prefers the kind of sequence that produces traces rather than the kind that gathers them back. There is a second layer to this question. It appears as soon as you look closely. Many of the fundamental rules we use to describe nature do not advertise a direction of time in the way our experience does. At the level of idealized motion, the difference between forward and backward can be surprisingly hard to detect. A clean collision replayed in reverse can look like another valid collision. A planet moving smoothly through space does not carry a label that says which way the story is supposed to run. And yet the world we live in is not a gallery of clean collisions. It is a world of countless degrees of freedom, a world of endless interactions, a world where events do not end when the main action ends. Even small events have a long tail, a trail of heat, scattered light, minute vibrations, rearranged molecules. This is why the arrow of time is often introduced with a humble image, not a cosmic one, not a galaxy, not a black hole, a glass of water. A single drop of ink falls into clear water. At first, it is concentrated, dark, unmistakable. Then it stretches curls and dissolves into finer tendrils. Soon, the water is stained throughout. What began as a sharp point becomes a diffuse presence. If you saw the ink gather itself back into a single drop, you would not merely feel surprised. You would feel that the world had broken one of its quietest promises. That promise is not written on the face of a clock. It is written in the way large systems behave, in mixing, in heating, in friction, in radiation, in the building of memory, in the long, slow evolution of the cosmos. And here, within the first minutes, we can place a fact that makes this story properly cosmic. The arrow of time does not begin in your kitchen. It begins in the early universe. However we choose to describe it, there is a deep sense in which the universe started in a special condition. It was a beginning that allowed the arrow to be drawn so clearly afterward. If the beginning had been different, the direction we take for granted might not have emerged with the same force. The world's records might not have formed the way they did. The traces we rely on to read the past from the present might not have accumulated so reliably. This is the route ahead. We will look up toward the early universe and ask what it means for a beginning to be special in a physical sense. We will come back down to ink in water, to heat in a room, and to the way memories can exist at all. We will see how the same logic repeats at different scales. Then we will return to the extremes: gravity, collapsing matter, the strange bookkeeping of black holes, places where the arrow of time becomes harder to ignore and harder to mistake for a mere habit of human perception. For now, hold two images together. The first is a reel of film being played backward. It is an illusion of reversal produced by perfect control over frames. The second is a universe that cannot be edited frame by frame. Every event writes itself outward into countless traces that do not come home. Somewhere between those two images lies the simplest question and the deepest one. Not why we can imagine time going backward, but why the world in practice keeps choosing forward. The ink and water feels like a small local promise, a promise made in a glass on a table. But the same kind of promise appears in places where no table has ever existed. Look up at the night sky, and you are looking into a layered archive. Some of the light reaching you tonight began its journey before cities existed. Some of it left its source before human beings had language. And behind that, deeper still, there's a faint, nearly uniform glow that arrives from every direction. That glow is not just scenery, it is a clue. It tells us that the universe had a hot, dense youth. It tells us that space has been expanding and cooling. And it tells us something else more subtle. The universe keeps producing records. It keeps leaving traces that can be read later from the present. This is part of what it means for time to feel like it has a direction. But here is the point that makes the story genuinely cosmic. The arrow of time does not only come from what happens, it also comes from what the universe was like at the beginning. There is a way to say this without equations. Imagine a deck of cards laid out in a perfectly ordered stack. Nothing about the laws of shuffling forbids the cards from returning to that exact order. But if you begin in a random jumble, you do not have a clean notion of becoming mixed. You are already mixed. In a similar way, the early universe appears to have begun in a state that was not simply generic. It began in a condition that made becoming more mixed possible in a vast, reliable way. This is where the word special enters the story. Not special in the sense of miraculous, special in the sense of constrained. A beginning can be constrained in ways that matter enormously later. It can be smooth in some respects, while still containing the small irregularities needed to build structure. It can be hot and dense while still leaving room for the creation of records as the universe expands and cools. When we say the universe started in a special condition, we are pointing to this kind of constraint. We are pointing to a beginning that does not look like an arbitrary snapshot taken from all possibilities. If that sounds abstract, return to the ink. A drop of ink in clear water is not a common arrangement. It is a poised arrangement. It is a moment with potential. From that poised moment, the story has somewhere to go. It can spread. It can leave a trail of finer and finer traces. It can turn a sharp distinction into a diffuse memory. The early universe, in a deep sense, played a similar role for everything that followed. It set the stage so that the cosmos could produce an arrow. Now, it is tempting to think that the arrow of time is simply the same thing as the expansion of the universe. Space gets larger. Time goes forward. End of story. But expansion is not the whole explanation. Expansion is part of the backdrop. The key question is why the universe, as it expands, keeps generating records in one direction rather than unmaking them. To see why that is not automatic, consider a different kind of universe. Imagine a universe that begins in a thoroughly typical state, with no particular constraint in the ways that matter for the arrow. In such a universe, there would be no strong global tendency for traces to accumulate in the same way. There might be local arrows here and there, brief and fragile. But the clean, persistent one we experience might not stand out. Our universe is not like that, at least not according to what its oldest light suggests. There's a faint background glow that is remarkably uniform, as if the early universe had been smoothed to an extraordinary degree. And yet the universe is not perfectly smooth now. Galaxies exist. Stars exist. Planets exist. Those two facts together are already a kind of signature. They hint at a beginning that was smooth enough to be low in a certain sense, while still carrying tiny variations that could grow into structure over cosmic time. This is the part of the story where people often say, "That sounds like entropy." And it is connected. But to keep the journey elegant, we can hold the idea in a simpler form for the moment. A special beginning gave the universe room to develop a clear direction, because it gave the universe room to create records. Those records show up as light traveling outward, as heat spreading as chemical histories written into matter, and as the slow gravitational shaping of structure. In other words, the arrow is not an added force. It is not a hidden engine pushing time forward. It is a pattern that becomes visible when a universe starts in a particular kind of state and then evolves under its ordinary laws. In the next step, we will return to the glass of water in a more careful way. We will ask what it means for one macroscopic state to have more room than another. We will keep it physical. We will keep it visual. And we will use that humble scene to build a bridge back to the early universe where the arrow of time first became possible. For now, keep the cosmic image steady, an expanding universe filled with lingering light, a universe that writes its history outward into traces, and a beginning that was constrained enough to let those traces grow in one direction instead of erasing themselves as quickly as they appear. The phrase, a special beginning, can sound distant. It can feel like something that belongs only to cosmologists and telescopes. So let's bring it down to a scale you can hold in your hands. Picture a clear glass of water on a table. The surface is still. The water looks uniform, almost empty of history. Now, a single drop of ink falls in. At first, it is unmistakable. A dense dark point. A small event with sharp boundaries. Then, the ink begins to move. It does not travel like a marble rolling across a floor. It unfurls. A thin thread stretches downward. It curls and folds as if it is riding with smoke underwater. The tendrils break into finer tendrils. The dark region loses its edge. After a while, the glass looks different in a quieter way. The ink is everywhere, and nowhere in particular. The water has a tint. The sharp point has become a diffuse presence. This is not a dramatic scene. It is gentle, even beautiful. But it carries a rule that is so consistent, we rarely think to name it. We expect the ink to spread. We do not expect it to gather itself back into a single drop. And if it did gather back, the surprise would not be only emotional. It would feel like a crack in our understanding of how the world keeps track of itself. Because the ink does not just spread through space, it spreads into detail. At the beginning, there is a simple description that fits what you see. A drop here, clear water there. A little later, the description needs more words. There are wisps. There are filaments. There are gradients of color. There are layers of turbulence, too small to name one by one. Even if you never measure a single molecule, the direction is visible. The scene becomes harder to compress into a simple statement. In a sense, the world has written more of itself into the glass. Now, it is important to be precise about what this image is and is not. The ink is not being pulled forward by time, as if time were a current. There is no forward force. What you are watching is a system with an enormous number of moving parts. Countless water molecules, countless ink molecules, all colliding, jostling trading energy, and carrying tiny bits of motion into tiny new places. Once that begins, the scene has many ways to continue. The ink can spread through the water by countless microscopic paths. It can reach the same overall look in many different ways. But the reverse story is strangely narrow. For the ink to return to a single drop, every little swirl would have to undo itself. Every tiny filament would have to retrace its own history. Every collision would have to line up just right, as if the glass were coordinating a choreography too intricate for any conductor. That is why the reversed movie is not the same as the reversed universe. If you record the ink spreading and play the footage backward, the gathering can look convincing. Your eyes can accept it. Your brain can accept it. Because the screen is handing you the perfect sequence. But in the real glass, the spreading does not stay inside the spreading. It leaves traces beyond what you are watching. There is heat exchanged with the air. There is vibration carried into the table. There is light scattering off the glass and into the room. There are microscopic ripples that die away, but do not vanish into nothing. They become part of the surrounding world. In other words, the event writes itself outward. This is the quiet bridge from the ink to the cosmos. The universe is not a sealed container with a clean boundary. Events do not remain self-contained. They broadcast. A star shines, and the light does not stay near the star. It travels outward, carrying a record of the conditions where it was made. A hot object cools, and the warmth does not stay inside it. It migrates into the surrounding world. The ink in the glass is the local version of that same habit. A compact difference tends to become a spread-out difference. A sharp boundary tends to become a gradient. A simple description tends to become a more detailed one. And this is why the ink is such a useful anchor. It shows the arrow of time without saying the word time at all. You can watch the arrow in the way the scene changes, from concentrated to diffuse, from few features to many features, from a clean contrast to a subtle tint. Now, return briefly to the early universe. In the first moments, the universe was hot and dense. Light and matter interacted constantly. Space was filled with a kind of restless glow. As the universe expanded and cooled, that glow was freed to travel. A record was released. Today, that record still exists as a faint background light arriving from every direction. It is one of the reasons the early universe is not only a theory, it is a chapter we can still read. The ink in water is not the same phenomenon as the early universe cooling, but the direction is the same kind of direction. A system begins in a condition that is constrained. It begins with a clear distinction that can be described simply. Then it evolves into a condition where the distinction is spread out and the description becomes more complex. This is the shape we will keep returning to. We will let the ink give us our physical intuition. Then we will use that intuition to interpret what the universe is doing on the largest scales. In the next section, we will set the ink beside other familiar one-way processes. Heat spreading through a room, friction turning motion into warmth, light leaving a source and thinning as it goes. It will still feel local and tangible, but the point will be cosmic. The universe behaves like a world that keeps writing records, and the arrow of time is the direction those records accumulate. Place the glass of water beside a few other scenes you already know. A kettle comes to a boil. Steam rises. Warmth spreads into the kitchen air. Later, when the heat source is gone, the room does not spontaneously return that warmth back into the kettle. A hand rubs against a tabletop. The motion slows, The surface warms slightly. What was clean movement becomes a thin veil of heat dispersed into the wood and the air. A candle burns. Light fills a space. The glow reaches walls, faces dust and distant corners. When the flame is extinguished, the light does not gather itself back into the wick. These are different processes, but they share a family resemblance. They all take something compact and structured and spread it out. They all turn a sharp distinction into a gradient. They all create traces that leak into the surroundings. And once those traces are out in the world does not neatly call them home. This is one way to recognize the arrow of time, not as a number on a clock, as a direction in which traces accumulate. The ink in water is a trace. Heat in a room is a trace. Scattered light is a trace. A faint vibration that fades into the table is a trace. Even a memory is a trace. A memory is not made of pure thought. It is made of matter in a particular arrangement, connections that change, patterns that stabilize, a physical record inside a living system. And like other records, it is not free. A memory is built and maintained by processes that exchange energy and leave heat behind. Even if the heat is too small to notice, the direction is the same. A trace is created, and it does not uncreate itself. When you collect these examples, you begin to see why forward feels so consistent. Forward is the direction in which the world keeps writing. Now, lift your attention back toward the sky. A star is not only a bright object, it is a machine that turns concentrated fuel into a flood of radiation. It takes ordered energy stored in nuclei and sends a long outward message into space. That message travels for years, centuries, and longer. It touches dust grains. It warms gas clouds. It nudges electrons. It bounces. It scatters. It spreads into wider and wider angles. This is the cosmic version of the candle. A young hot planet cools. A cloud collapses and heats then shines. A supernova flashes and leaves expanding debris and a changed chemistry behind. Again and again, the story has the same direction. The universe makes concentrated differences. Then it spreads them into traces. It might be tempting to say that this is simply because the universe is expanding. Space gets larger, so everything gets diluted. Light thins. Heat disperses. But notice that even in a sealed room, without any cosmic expansion, heat still spreads. Even in a glass of water, without any galaxies, the ink still disperses. So the arrow is not only about expansion, it is something more general. The arrow is about what happens when many degrees of freedom interact. When countless microscopic motions combine into a macroscopic scene. In those situations, sharp patterns tend to soften. Distinct differences tend to become shared differences. And the world tends to generate records that are easier to create than to erase. This is why the arrow of time is so hard to avoid. It is in the kitchen and in the cosmos. It is in friction and in starlight. It is in chemistry and in memory. Now there is a subtle point hiding under the simplicity. When we say these processes are one way, we do not mean that they are magically forbidden to reverse. We mean that the world does not naturally arrange itself to reverse them. A room could in principle gather its warmth into one corner. A glass of water could in principle gather its ink into a drop. A scattered beam of light could in principle converge back into a single filament. But in practice, the world does not do this. Not because it is lazy, because it is busy. Every process is happening alongside countless other processes. Every event shares the stage with an environment, and the environment is always accepting traces. This is the bridge we need. Before we return to the deeper paradox, the laws of motion at the smallest scales can look indifferent to time's direction. And yet the arrow in large systems is everywhere. So the question tightens. If the arrow is not an extra force and not merely a habit of clocks, why is it so reliable? Why do traces accumulate so consistently? Why does the world keep writing forward? In the next section, we will move toward that paradox directly. We will look at the strange fact that many fundamental descriptions of nature can run either way, at least on paper. And then we will ask what changes when a process stops being clean, isolated, and small, and becomes the kind of process that fills a kitchen or a planet or a universe. The arrow of time feels absolute in daily life. Ink spreads, heat disperses, light travels outward, memories point in one direction. So it can be surprising to learn that many of the basic rules used in physics do not announce an arrow in the same way. This does not mean the universe is confused. It means our experience of direction is not written plainly into every equation at the smallest scales. Begin with a clean, idealized scene. Two smooth objects collide on a perfectly frictionless surface. They meet, exchange motion, and separate. If you watch that collision in reverse, you would still see two objects approach, meet, and separate. Nothing about the reversed motion looks obviously impossible. Or picture a planet moving through empty space, far from any atmosphere, far from any friction. Its path can be traced forward and it can be traced backward. The geometry alone does not mark one direction as the only legitimate one. These examples are not meant to deny the arrow you see in the glass of water. They are meant to isolate the puzzle. If the smallest pieces can, in principle, move in ways that look valid both forward and backward, why do large systems behave so differently? Why does a room not gather its heat back into one corner? Why does a scattered beam of light not reassemble into a clean ray? Why does ink not return to a single drop? One easy answer is to say that the reverse would require an astonishing level of coordination. That is true, and we will come back to it. But first, let's make the contrast sharper, because it matters for the tone of the whole story. A reversed movie is an artifact of editing. When you reverse a recording, you are not asking the world to undo itself. You are asking a device to show you frames in a different order. The device is perfectly happy to do that. The deeper question is whether the world itself can run backward without that external editing. To run backward, in that physical sense, the entire process would need to reverse, including its faintest side effects. Not only the main action, but everything it disturbed. That includes heat. That includes scattered light. That includes tiny vibrations that traveled into the surroundings. And once you include those side effects, the clean collision is no longer clean. It becomes part of a much larger system. This is where the arrow begins to appear. A microscopic description can look symmetric, but a macroscopic event is rarely microscopic. It is a huge aggregation of microscopic interactions. A shattering glass is not only the motion of a few visible fragments, it is also the ripples of sound in the air. It is the heat produced at countless microcontacts. It is the deformation of materials. It is the scattering of light off sharp edges. All of those channels carry away detail, and that detail matters. When we say time has a direction, we are often pointing to the fact that detail spreads into places where it becomes hard to gather back into a single coherent story. This is an important shift. The arrow is not primarily about whether motion can be reversed in principle. It is about whether the world can recover the fine-grained detail that was scattered into the environment. Now, there is a famous place where the contrast becomes almost philosophical. Suppose you could pause time at the moment the ink has formed a delicate set of tendrils in the water. Suppose you could see in perfect clarity every microcurrent and every microscopic motion. If you could then reverse every one of those motions with perfect precision, the tendrils would reform into the drop. The ink would gather. The glass would look as it did before. The laws at that level do not forbid it. So why does it not happen? Because perfect precision is not a feature of the world we inhabit. It is a feature of idealization. In the real world, the ink is not isolated. The glass is not isolated. The room is not isolated. The event is always exchanging minute traces with the rest of the universe. Even if those traces are too small to notice, they are enough to break the possibility of spontaneous reversal. A tiny extra vibration, a tiny stray photon, a tiny difference in temperature. Once those differences exist, the reverse story is no longer the same story. It becomes a different branch of events. So, the paradox can be stated in a clean, calm way. At the microscopic level, the basic rules can be compatible with both directions. At the macroscopic level, the world behaves as if one direction is overwhelmingly favored. The arrow is not a contradiction in the laws. It is a consequence of what happens when those laws act on large systems that are never perfectly isolated. In the next step, we will return to the ink and make one idea precise without turning it into a lecture. We will not use formulas. We will use a kind of counting you can feel. We will ask why ink spread out seems to have more room to exist than ink gathered into a drop. Why the world has many ways to continue forward from a concentrated state and so few ways to continue backward. That is where the arrow becomes less mysterious. Not because we have added a new force, but because we have learned what a large system is allowed to do and what it is allowed to forget. Return to the glass. The ink has already softened into a web of threads. Some strands are darker. Some are lighter. Some curl downward. Some fan outward. Nothing about this looks like a single simple motion. It looks like a crowd. Now, without using any equations, we can still ask a question that has the flavor of counting. How many different microscopic stories can produce a scene that looks like ink spread throughout water? There are many. The tendrils can twist in countless patterns. The tiny currents can take countless routes. The ink molecules can arrive at similar overall shapes by an enormous variety of paths. If you only care about what your eyes can see, the end result is forgiving. You do not need one exact microstory. You can reach a similar macroscopic look through a vast family of micro-stories. This is what more room means in a physical sense. A macroscopic state like ink spread out has room to exist because there are countless fine-grained ways for the world to realize it. Now compare that with the beginning. At the start, the ink is a compact drop, a single dark point cleanly separated from the clear water. That scene is not forgiving. There are not many microscopic stories that look like that for long. To keep the ink as a neat drop, the microcurrents must keep canceling. The collisions must keep balancing. The smallest motions must keep lining up so that the boundary stays sharp. In other words, the compact drop is a narrow corridor in the space of possibilities. The spread out ink is a wide plane. This is not a moral statement about disorder. It is not a claim that the universe prefers mess. It is a statement about options. Forward has many options. Backward has few. This is why the arrow of time can feel inevitable without being forced. When you have a system with countless moving parts, it does not need a push to drift into the wide plane. It only needs to not be perfectly arranged to stay in the narrow corridor. Now bring the movie back into the picture. When you reverse the footage of ink dispersing, you are watching a path that has been curated. You are watching one exact micro-story played backward. It can look natural because you are seeing a coherent sequence, but the world does not have a curator that selects the one backward path and keeps it stable against every disturbance. The real glass is open to the room. The room is open to the building. The building is open to the planet's atmosphere. And the planet is open to space. At every boundary, tiny exchanges happen. Heat leaves. Heat enters. Light scatters away. Vibrations fade into materials. Each exchange is small, but each one changes the fine detail. And once the fine detail changes, the backward path is no longer the same path. This is the quiet power of more room. A wide plane is robust. You can step onto it from many directions, and small disturbances still leave you somewhere on the plane. A narrow corridor is fragile. A small disturbance moves you away from it. So the ink spreads, not because it must, but because it can. It has countless ways to continue in that direction. Now, if you want a single sentence that captures the logic, it is this: the arrow of time is the direction in which the world has vastly more ways to be. Notice how this reframes the paradox from earlier. The microscopic rules do not need to contain a built-in arrow. The arrow can appear when you look at collections of microscopic rules acting together, because collections create a landscape of possibilities, a landscape with planes and corridors, a landscape where some macroscopic scenes can be realized in countless microscopic ways, and others can be realized only in exquisitely tuned ways. Once you see the landscape, you can also see why the arrow is so stable. It does not take much for a system to leave a narrow corridor. It takes an extraordinary level of coordination to enter it. Now turn your gaze back toward the early universe, because this is where the same logic becomes grand. A special beginning is like a corridor. It is a constrained starting point. It is a macroscopic condition that does not have the same room as all other possible conditions. From that constrained beginning, the universe had somewhere to go. Not because it was pushed, but because the landscape ahead was wide. As the universe expanded and cooled, it produced more ways for traces to exist. light could travel freely, heat could spread, structures could form, records could accumulate. The arrow of time in this view is not a mysterious wind at your back. It is the shape of the landscape the universe moves through. In the next section, we will focus on something that makes the arrow even harder to reverse in practice. It is not only that spread out states have more room, it is that spread out states leave fingerprints everywhere. They write their history into the environment. And once the history is written into the world around the event, the world becomes part of the story. That is where reversal stops being merely unlikely and starts becoming, for all practical purposes, unreachable. The ink has spread, but the spreading does not stay inside the glass. That is the detail that quietly changes everything. As the tendrils form, heat is exchanged with the surrounding air. Light reflects off the glass and scatters into the room. Tiny vibrations travel through the table and fade into the building. Molecules at the surface trade energy with molecules beyond the surface. Each of these effects is small. None of them feels dramatic. But together, they mean the event does not belong to the glass alone. It belongs to the world around it. This is what physicists mean in a very ordinary sense by information. Information is not a message with words. It is a physical imprint, a difference that can be detected in principle somewhere in the universe. The color of the water carries information about where the ink has been. The warmth of the air carries information about energy that is moved. The scattered light carries information about shapes and motions that existed a moment earlier. Once these imprints exist, the past is no longer confined to one place. It has been copied outward. Now return to the idea of reversal. To truly reverse the spreading of the ink, you would need more than a backward flow inside the glass. You would need to gather every imprint the event has left behind. The heat would need to return from the air into the water in just the right pattern. The scattered light would need to reconverge along its original paths. The tiny vibrations would need to reassemble and flow back into the exact motions that created them. This is the difference between reversing an image and reversing a world. A video file stores a limited curated set of information. It shows you what a camera captured and nothing more. When you reverse it, you are simply rearranging that stored data. The world does not store its events in a single file. It stores them in everything they touched. This is why the arrow of time feels stronger when you think in terms of traces rather than motion. Motion can in principle be reversed. Traces once distributed do not politely line up to be recalled. Now place this idea beside a familiar experience, a memory. A memory feels internal, almost private. But it is a physical process. It is a particular arrangement of matter in a brain. Connections that have changed strength. Patterns that have stabilized long enough to be used again. To create and maintain those patterns, energy is exchanged. Heat is released. Chemical gradients shift. The act of remembering leaves traces beyond the memory itself. This is why memory points in one direction. Not because the brain has access to a special clock, but because memory is built by processes that write information into the world. The same logic holds for photographs, notebooks, and data stored on a disk. All of them are physical records. All of them exist because something else changed to make room for them. Once a record exists, undoing it is not just a matter of reversing the visible change. It requires undoing all the changes that supported it. This is the deeper meaning of irreversibility. Irreversibility does not mean forbidden by law. It means entangled with too much of the world to be practically undone. Now lift this idea to the cosmic scale. A star shines. The light leaves the star and travels outward for years, centuries, and longer. Along the way, it interacts with dust gas and magnetic fields. It changes trajectories. It changes frequencies. It becomes part of other processes. The star's history is no longer stored in one place. It is scattered across space. The early universe did something similar on a grand scale. As it expanded and cooled, light was released. That light traveled freely for the first time. It carried a snapshot of conditions from a very early moment. Today, that snapshot still exists as a faint glow across the sky. To reverse that moment, the universe would need to gather that light back. It would need to undo every interaction the light has had since it was freed. It would need to recall a record written across billions of light years. This is not a poetic obstacle, it is a physical one. The arrow of time becomes firm because the universe does not erase its notes as it goes. It keeps them. Each event adds lines to the ledger. Each interaction spreads the story further outward. This is also why small systems can sometimes behave differently. In a tiny, well-isolated system, there may be few places for traces to go, few channels for information to leak away. In such cases, reversals can appear briefly and delicately, but the moment a system is embedded in a larger environment, the balance changes. More channels open, more records are written. The world gains more copies of what happened. And once the copies exist, the past becomes anchored. This is the quiet reason the arrow of time feels so dependable. It is not because the universe forbids reversal in principle. It is because reversal would require the coordinated recall of information that has been spread too widely. The ink has not just moved. It has told its story to the room. The star has not just shone. It has told its story to the galaxy. In the next section, we will return to the early universe with this idea in hand. We will ask why gravity of all forces changes the story of traces and records in such an unexpected way. Why a universe that began smooth could still grow complex structure, and why that growth does not erase the arrow but sharpens it. For now, keep one thought steady. Time feels one way because the world remembers. If time feels one way because the world remembers, then the next question is unavoidable. Why does the world have so much room to remember in the first place? Why is there such a persistent direction in which traces accumulate rather than a balance where traces are made and unmade with equal ease? This is where the story returns to the beginning, not the beginning of a day or a century, the beginning of the universe. The oldest light we can see does not arrive as a chaotic storm. It arrives as a calm, nearly uniform glow across the sky. A background so smooth that its irregularities have to be teased out with careful measurement. That smoothness is already a clue. It suggests that the early universe was not an arbitrary snapshot drawn from every possibility. It suggests constraint, and constraint is exactly what an arrow needs. Return to the glass for a moment. A neat drop of ink in clear water is a constrained beginning. It is not the most typical arrangement the ink and water could have. It is a poised arrangement with room to evolve into countless more detailed scenes. A beginning like that creates a direction, not by force, but by opportunity. The early universe appears to have played the same role. It began in a state that allowed a clear arrow to emerge as time went on. It allowed the universe to create more and more records in a consistent direction. If the beginning had been thoroughly typical in every relevant sense, the arrow would not stand out so cleanly. There might be local arrows temporary and fragile, but the grand reliable arrow we experience might not be so deeply written into the cosmos. So when we say the arrow of time begins in the early universe, we are saying something quite specific. We are saying that the universe began in a condition that was unusually ordered in the ways that matter for the creation of records. That can sound strange, because the early universe was also hot. It was dense. It was full of radiation and particles colliding constantly. How can something that hot be described as ordered? Here is the key that keeps the story elegant. Order in this context is not the same as neatness. It is not the same as a tidy room. The relevant idea is not whether the early universe looks simple to the eye. It is whether the universe began in a configuration that left room for traces to spread and multiply afterward. A smooth beginning is one of those configurations. In a smooth universe, small differences have room to grow. Heat can flow. Light can travel. Structures can form. Records can accumulate. In a universe that begins already maximally scrambled in the relevant ways, there is less room for an arrow to develop. Not because events cannot happen, but because there is no clear global direction for the growth of records. Now, a careful listener might notice a tension. A smooth beginning sounds in a way like evenly mixed. An earlier, evenly mixed sounded like the end state of ink in water. So why does smoothness in the early universe act like a low beginning rather than a high ending? The answer is that the universe is not only ink and water. The universe also has gravity. And gravity changes what room to evolve means. In an ordinary fluid, without gravity, spreading out is the easy direction. Uniformity is the wide plane. But when gravity is part of the story, uniformity can become a kind of precarious balance. A smooth distribution of matter is not necessarily the final state. It can be the starting point for a long cascade of structure. Tiny variations grow. Regions become slightly denser. Those regions attract more matter. Over time, the smoothness breaks into a rich, uneven architecture. Stars, galaxies, clusters. And this does not erase the arrow of time. It strengthens it, because every step of that growth produces more ways for records to be written. Light is emitted. Heat is transported. Matter changes chemically. Radiation streams outward. The universe does not merely rearrange itself. It documents the rearrangement across space. So the early universe matters because it sets the initial conditions for this entire chain. It sets the stage for an arrow that can be amplified by gravity, not canceled by it. A constrained beginning is not the full explanation, but without it, the rest of the explanation has nowhere to stand. This is why cosmology belongs near the front of the story. The arrow of time is not a local quirk that happens to be everywhere. It is a global theme written into the universe's history from its earliest chapter. In the next section, we will focus on gravity directly. We will see why gravity flips everyday intuition, why a universe that began smooth could still be low in the relevant sense, and why the growth of cosmic structure is not a reversal of the arrow, but one of its grandest expressions. For now, keep the image steady. A young universe smooth enough to be constrained. Tiny irregularities waiting like faint ripples. And a future filled with the widening spread of records written outward into the dark. In the glass of water, uniformity feels like the end of the story. Ink spreads until the difference is shared everywhere. The scene becomes calm. The sharp edge disappears. So it can be natural to carry that intuition upward and assume the early universe being smooth must have been already finished in the same sense. Gravity is the reason that intuition breaks. Gravity does not treat smoothness as an endpoint. It can treat smoothness as a balance that will not last. To see why, imagine a perfectly even fog filling a vast room. If nothing attracted anything else, the fog would remain even. But if each tiny part of the fog pulled on every other part, then a small irregularity would matter. A slightly denser region would pull a little more strongly. It would draw in a little more material. That extra material would make it denser still. What begins as a whisper becomes a drift. What begins as a drift can become a collapse. This is not a dramatic claim about violent chaos. It is a quiet claim about patience. Gravity is patient. Given time, it amplifies small differences. This is why a smooth, early universe can still be a beginning with room to evolve. It is why uniformity under gravity is not the wide plane you might expect. It is closer to a poised surface, a surface that can ripple into structure. Now look at what happens when structure forms. Gas falls inward. As it falls, it heats. It glows. It begins to shine. Stars ignite. They turn concentrated fuel into radiation that streams outward. They build heavy elements. They change the chemistry of their surroundings. Galaxies assemble. They stir gas drive shocks and generate vast webs of motion. Over time, they become sources of light heat and information that travel far beyond their own boundaries. None of this is the universe reversing its arrow. It is the universe finding more ways to write records. A smooth universe has fewer visible features to record. A structured universe has many. A structured universe has gradients, boundaries, events, sources, signals, and each signal carries history outward. So gravity does not compete with the arrow of time. It provides one of the grand mechanisms by which the arrow becomes legible. Now there is an even subtler point here, and it matters for the elegance of the explanation. When people first hear entropy, they often imagine it as a single universal measure of mess. They imagine that more entropy always looks like more uniform. But gravity teaches a different lesson. Under gravity, a clumped universe can be, in an important sense, a universe with more room, more ways to arrange itself, more ways to distribute energy, more ways to radiate, more ways to carry traces outward. The ink story was about a difference spreading into a fluid. The gravity story is about differences growing into architecture. Both stories share the same direction. In both, the universe expands the space of what can happen. In both, the universe generates more channels for traces to exist. This is why the arrow of time is not merely a drift toward bland sameness. In a gravitational universe, the arrow can look like complexity. It can look like the birth of stars. It can look like the formation of galaxies. It can look like the slow knitting of structure across cosmic distances. And yet, beneath that complexity, the arrow remains the same kind of arrow you saw in the glass. In each case, a constrained beginning evolves into a state where there are many more ways for records to be written. Now, connect this back to the early universe. We see evidence that the early universe was remarkably smooth. We also see evidence that it contained tiny variations. Those variations were the seeds. Gravity took those seeds and over immense times cultivated structure from them. The result is the universe you can observe now. A universe filled with sources and signals. A universe in which past events do not stay local. They radiate. They imprint. They travel. This is the sense in which smoothness at the beginning can be low in the relevant way. Not low because it was quiet in every detail, but low because it left room for a long evolution that would create more avenues for traces. If you want a single image to hold, let it be this. The ink in the glass spreads until it is everywhere. Gravity in the universe gathers matter until structure appears. One story spreads. One story gathers, but neither story is about turning back. Both are about the growth of records, and the records are what make the direction visible. In the next section, we will go to the most extreme form of gravitational structure, a place where the idea of records becomes almost unsettling, a place where information seems to fall behind a boundary and where the arrow of time feels sharp. Black holes, for now, keep the bridge intact. The arrow of time is not simply the universe smoothing out. It is the universe creating and then distributing the traces of what happens. Gravity does not erase that. Gravity writes in a bolder ink. If gravity writes in bolder ink, then black holes are where the writing becomes impossible to ignore. They are not introduced here as monsters or mysteries. They are introduced as bookkeeping devices. A black hole forms when matter collapses so deeply that a boundary appears, a surface beyond which ordinary signals do not return. That boundary changes how records are kept. Consider what happens as matter falls inward. Gas spirals. It heats. It radiates. Light streams away, carrying information about the infall. The surrounding region is flooded with signals that tell a detailed story of what just occurred. Even before anything crosses the boundary, the arrow is already visible. Energy spreads. Radiation escapes. The environment gains copies of the event. Now focus on the boundary itself. Once matter passes it, there is no simple way for the outside world to recover the fine detail of what crossed. The record does not vanish, but it becomes inaccessible in the ordinary sense. This is not a philosophical claim. It is a practical one. Signals that could carry detail back do not make the return trip. From the outside, the story simplifies. The black hole can be described by a small set of properties: mass, rotation, charge. The intricate history of how the matter arrived is no longer readable in the same way. This compression of description is another mark of the arrow. A complex event has occurred. Many degrees of freedom have been involved, but the outward-facing record has become simpler, not richer. That simplicity does not mean less entropy in the broader sense. It means the detail has been displaced beyond reach. The universe has not erased the past. It has relocated it. Now place this beside the ink. When ink spreads in water, the detail does not disappear. It is distributed into finer and finer patterns, into places that are harder to track and harder to reverse. A black hole performs a similar move, but more decisively. Detail is not only spread, it is screened. This is why black holes feel like punctuation marks in the story of time. They mark events that cannot be neatly undone, not because of a special law that forbids reversal, but because the path back would require access to information that is no longer available to the rest of the universe. Now step back. A star forms, shines, and dies. Its death may seed new generations of stars. Its light travels outward. Its elements are dispersed. Each step adds to the ledger of traces. A black hole sits at the end of some of those paths. It gathers matter. It gathers energy. It gathers history. And in doing so, it sharpens the asymmetry between past and future. From the outside, you can say what a black hole is now. You cannot reconstruct in detail how every piece arrived. The arrow is not subtle here. It is embedded in the structure of space-time itself. This does not mean black holes violate the basic rules we discussed earlier. They are built from them. The microscopic laws remain intact. What changes is the scale and the connectivity. Once an event is entangled with a black hole, the environment that would need to coordinate a reversal becomes unimaginably large. Reversal would require not only the recollection of scattered traces, but the recovery of detail from behind a boundary. At this point, the idea of running the universe backward stops being a thought experiment and becomes an abstraction. It is no longer about whether the laws allow it in principle. It is about whether the universe provides the access it would require. And here, the answer is clear. The arrow of time is reinforced by the way extreme gravity organizes information. It channels events into forms that are easy to describe going forward and impossible to reassemble going backward. Now connect this back to the beginning. A universe that starts smooth has room to create structure. Structure creates events. Events create traces. Gravity amplifies the spread and sequestration of those traces. Black holes are not anomalies in this picture. They are endpoints. They are places where the logic of the arrow is made explicit. The past does not disappear. It becomes unreachable. This is why discussions of time so often end up here, even when they begin with something as gentle as ink and water. The arrow that starts as a soft tendency becomes under gravity a firm boundary. From the perspective of the universe, this is not a failure of symmetry. It is a consequence of history, a history that began in a constrained state, a history that evolved into complexity, a history that now contains places where the return path is closed, not by decree, but by structure. In the next And final step, we will pull back one last time. We will ask whether there are any exceptions to this picture, whether small systems can ever seem to step against the arrow, and why those exceptions do not threaten the broader story. For now, hold the image of a boundary, a place where matter crosses, signals fade, and the past becomes part of the universe in a way that cannot be neatly reversed. Here the arrow of time does not whisper. It stands. After ink, after stars, after black holes, it is natural to ask a careful question. Are there any places where the arrow of time weakens? Are there moments when the world seems to hesitate as if it might step backward? There are, not in the sense of a cup unshattering in midair, not in the sense of a galaxy unforming, but in small, sheltered corners of physics, the arrow can look less rigid. The simplest way to understand this is to think again in terms of room. A large system has an enormous environment. It has countless channels through which traces can be written outward. Heat-light vibrations, microscopic rearrangements. A small system has fewer channels, fewer places for traces to go, fewer ways for the world to make copies of what happened. In such a system, it can be possible to see brief fluctuations that look like a tiny step against the usual direction. A small cluster of particles may momentarily become more ordered. A local gradient may sharpen for a short time before softening again. A system may wander into a configuration that resembles its past. These are not miracles. They are part of the same landscape we have been describing. When the landscape is small, wandering can bring you back near where you started. But notice what is missing. The moment you connect that small system to a larger environment, the wandering changes character. More channels open, more traces are written, more fine detail is shared with the outside world. And once the outside world has received those traces, a return is no longer a simple return. It would require the outside world to cooperate. This is the heart of the second counting by image. As you increase the size of a system, you are not only adding more particles, you are adding more ways for detail to escape. You are adding more places where the story can be recorded. A small system can be like a conversation in an empty room. It is possible in principle to replay it. It does not touch very much beyond itself. A large system is like a conversation in a crowded city. Words bounce off walls. They are overheard. They are distorted by wind and traffic. They are recorded by devices you do not control. To reverse the conversation, you would need to reverse the entire city. This is why the arrow becomes so firm at the scale of daily life and cosmic history. It is not only that spread out states have more room, it is that large systems are embedded in environments that collect traces. The environment makes the arrow sturdy. Now a listener might object, if small systems can fluctuate, why can a large system not fluctuate in the same way, just less often? Here is the gentle answer without numbers. A large system is not simply a small system repeated many times. It is a system that is constantly producing and exporting traces. It is constantly multiplying its records. A fluctuation in one corner would need to be matched by coordinated fluctuations everywhere else that has absorbed its traces. The ink would not only need to gather inside the glass, the room's heat would need to gather as well. The scattered light would need to reconverge. The vibrations in the table would need to reverse their fading. As the system grows, the list of also grows. Also the air, also the table, also the walls, also the planet, also the surrounding radiation field. This is the practical meaning of the arrow being stable. A small system can step sideways in the landscape. A large system would have to move the landscape with it. So yes, there can be delicate exceptions. In carefully controlled experiments, physicists can sometimes coax systems into behaving in ways that look like a partial undoing. A pattern reappears. A signal refocuses. A process retraces a path for a moment. But these are not the universe turning around. They are the result of isolation and control. And notice the deeper point. The existence of these exceptions actually supports the broader story. It shows that the arrow is not a mystical decree. It shows that the arrow depends on how open a system is, how many channels exist, and how widely traces spread. When traces are contained, reversals can be staged. When traces are distributed, reversal becomes unreachable. Now bring this back to the documentary view of the cosmos. The universe is the largest system. It has no external environment to hand its traces to, but it also contains every environment within itself. Every event writes into some other region. Every photon that leaves a star becomes part of the universe's record. Every cooling process leaves a trail. Every gravitational collapse reshapes what can be known from where. There is no outside editor, no external hand to gather the traces back. So the universe does not turn around as a whole. It does what large systems do. It continues to generate records in the direction that has more room. In the final section, we will hold the entire picture at once. A special beginning, a landscape of possibilities, traces spreading into the environment, gravity shaping structure, black holes sharpening the boundary between what can be recovered and what cannot, and from that, a calm conclusion. Time moves forward, not because the universe is compelled by a hidden engine, but because the universe has learned how to remember. Now, we can hold the story in a single frame, not as a proof, as a map. The question was simple to ask. Why does time only move forward? And the answer is not a single mechanism. It is a set of layers that reinforce one another. The first layer is cosmic. The universe began in a condition that was constrained. A beginning smooth enough to be special, and yet not empty of detail. A beginning that left room for an arrow to be drawn clearly afterward. As the universe expanded and cooled, it freed light to travel. It allowed records to persist. It gave history a way to be carried outward into space. That is the first layer. A special beginning, followed by a universe that continually writes traces. The second layer is local. In the glass of water, the ink does not spread because time pushes it forward. It spreads because there are many more microscopic stories that look like spread out than stories that look like gathered into a drop. Forward has room. Backward is a narrow corridor. And once the ink spreads, it does not only change the water, it changes the world around the water. Heat drifts into the room. Light scatters into countless paths. Tiny vibrations fade into material. The event becomes a record distributed across its environment. That is the second layer. Large systems have many degrees of freedom and many channels for traces to be written outward. The third layer is gravitational. Gravity changes what room looks like on the largest scales. A smooth universe is not necessarily a finished universe. Under gravity, smoothness can be a poised state. Small variations grow, matter gathers, structure appears, stars ignite and shine, galaxies assemble and evolve, radiation streams outward and carries history with it. Gravity does not erase the arrow. It makes the arrow easier to read because it creates more events and more records. And at the far edge of gravity, black holes make the asymmetry even sharper. They do not end the story. They archive it. They create boundaries where fine detail is not simply scattered, but screened. They turn the return path from difficult into, for all practical purposes, unreachable. So the arrow of time is not a single arrow carved into the laws. It is an arrow that appears when laws act on a universe that began in a special way and that then evolves through a landscape where traces spread and accumulate. This is why the reversed movie remains an illusion. A film can be reversed because the record is stored in one place and can be rearranged. The universe cannot be reversed in the same way because its records are not stored in one place. They are stored in everything. Now it is worth making one final clarification. Nothing in this picture requires time to be a substance flowing like a river. Nothing requires a hidden engine that forces the future to arrive. The arrow is a pattern that becomes visible when you look at many interacting parts and at how those parts leave imprints on one another. If you want a single phrase to hold on to, it can be this: time feels one way because the universe keeps writing and it does not unwrite what it has written. You can see it in the ink. You can see it in the warmth of a room. You can see it in starlight traveling outward. You can see it in the sky's oldest glow. And you can see it in the long arc from a smooth beginning to a structured cosmos where records accumulate across immense distances. So when you feel the forwardness of time in your own life, that feeling is not separate from the universe. It is a local expression of the same global story, a constrained beginning, a widening landscape of possibilities, traces spreading into environments, gravity amplifying structure, boundaries that make return paths fade. That is the map. And the map does not take away the wonder. It sharpens it, because it means the arrow of time is not a small quirk of human perception. It is a signature of a universe that has a history that can be read and that can be remembered. The ink does not gather back into a drop. The light does not return to its source. The sky does not forget its earliest glow. And that is why, in practice, time keeps choosing forward. There is one last image worth keeping, not because it is comforting, but because it is clarifying. A universe does not only contain events, it contains the ability to carry them forward as traces. Light travels, heat spreads, matter changes form, and keeps the marks of those changes. And because those marks persist, the present can hold evidence of what came before. That is what makes time feel like it has a direction. In the beginning of this journey, the distinction was simple. A reversed movie is not the same thing as a reversed universe. A movie is a controlled sequence stored in one place. It can be rearranged. It can be played backward. The universe is not stored in one place. Its records are distributed into air, into dust, into radiation, into the fabric of space between things. Once distributed, they do not line up again on command. That is the quiet reason the arrow is so consistent. Not because nature is enforcing a rule with a stern hand, but because nature is constantly writing into many pages at once. And the more pages there are, the more stable the story becomes. This is why the question, why time only moves forward, takes us from a glass of water to the oldest light in the sky. Because the arrow is not a local habit, it is a global history, a beginning that was constrained, a universe that expanded and cooled, a world where traces could persist and travel, a gravitational architecture that grew from tiny variations into stars and galaxies, and at the extremes, boundaries where fine detail becomes screened from ordinary recovery. All of it from the smallest scale to the largest points to the same practical outcome. Forward is the direction in which records accumulate. If you return once more to the ink, the scene is almost too ordinary to be philosophical. A drop becomes threads. Threads become a tint. A sharp difference becomes a diffuse one. But inside that ordinariness is the same logic that lets cosmology exist as an observational science, because the sky itself is a record. When you look at starlight, you are receiving a message that has been traveling for years. When you look at the background glow of the early universe, you are reading a page that has been open for a very long time. Time moves forward in practice because those pages keep being written, and the writing does not gather itself back into blankness. The arrow is what makes the universe legible, and that legibility has a strange implication. The past is not gone. It is embedded, not as a place you can return to, but as a pattern you can sometimes read from the traces it left behind. That is a calm kind of meaning, and it does not require any extra mysteries. Just a universe that begins in a special way, evolves under ordinary laws, and keeps its records distributed across space. If you replay the journey in a single line, it is this: a special beginning gave the arrow room to exist. Many interacting parts gave the arrow a landscape of possibilities. Traces once spread gave the arrow durability. Gravity gave the arrow a grand stage. And with that, the direction we call forward becomes less of a question mark and more of a signature. A signature written into ink, written into heat, written into starlight, written into the shape of the cosmos